You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Security Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. High Availability HA refers to architectural design focused on maintaining service continuity even when failures occur. Rather than preventing every possible outage, HA ensures that systems remain functional by incorporating redundancy, rapid recovery, and robust operational planning. The core idea is resilience, accepting that hardware, software, or network failures will happen, but ensuring they do not disrupt critical services for long. Organizations that depend on online platforms, financial transactions, or healthcare systems view HA as essential. In these environments, downtime translates directly to financial loss, safety risks, or reputational damage. HA is not a single tool, but a strategy woven into every aspect of system architecture. Basic HA concepts include redundancy, failover, and graceful degradation. Redundancy means having extra resources, whether servers, storage, or network paths, that can step in if the primary fails. Failover is the automatic redirection of traffic or workloads to these backup systems, ideally without noticeable interruption to users. Graceful degradation refers to systems continuing in a reduced capacity if not all components remain operational. For example, a video service may drop to standard definition if high-resolution nodes fail. Together, these concepts ensure that services remain available, even if not always at full capacity. The emphasis is always on continuity rather than perfection. Availability is often measured with formal metrics. Uptime percentages like 5 nines, 99.999% availability, quantify how often a system is expected to be accessible, often tied to service-level agreements. SLAs. Mean time between failures, MTBF, estimates how long a component or system can run before failing, while mean time to repair, MTTR, reflects how quickly systems can recover. These metrics guide design decisions, showing where investments in redundancy or faster recovery yield the greatest impact. For critical industries, even a few minutes of downtime may be unacceptable, meaning HA architectures must be engineered with rigorous reliability expectations and validated through consistent measurement. Recovery objectives are another foundational concept in HA. Recovery time objective, RTO, specifies how quickly a system must be restored after an outage, while recovery point objective, RPO, defines how much data loss is tolerable in terms of time. For example, an RPO of 1 minute means replication or backups must ensure no more than 60 seconds of data is lost. RTO and RPO drive architectural choices, such as synchronous replication or hot standby servers. They also influence cost. Tighter objectives require more investment. By defining RTO and RPO upfront, organizations ensure HA systems align with actual business tolerance for disruption. Redundancy can be implemented in different ways, with active-active and active-passive being the most common models. In active-active, all redundant components run simultaneously, distributing traffic and sharing load. This improves both availability and performance, since resources are always utilized. In active-passive, a backup system remains idle until the primary fails, at which point it takes over. While active-passive is often less expensive, failovers may cause brief interruptions. Active-active designs demand more complex synchronization and monitoring, but deliver seamless experiences. Choosing between these models depends on workload criticality, budget, and the tolerance for potential downtime during failovers. State synchronization and replication consistency are crucial in HA setups. Systems must ensure that backup nodes contain the same data and state information as primaries, so failover does not result in inconsistency. Synchronization can be synchronous, with updates applied simultaneously across nodes, or asynchronous, where replication lags slightly behind. Inconsistent replication can cause data loss or corruption during failover, undermining availability goals. For example, a financial transaction system must guarantee consistency across nodes, while a web cache may tolerate slight divergence. HA architecture requires careful planning of synchronization models, ensuring consistency matches the business needs for accuracy and resilience. Load balancing is one of the primary mechanisms for distributing traffic and ensuring HA. Load balancers distribute requests across multiple servers or services, preventing any single component from becoming overwhelmed. They can detect when a server fails and automatically redirect traffic, keeping the service uninterrupted. Load balancing also supports scalability, as more servers can be added behind the balancer to handle growth. Modern architectures may use global load balancers to distribute traffic across regions, combining performance optimization with resilience. Without load balancing, HA designs risk bottlenecks or overloads. With it, availability becomes an orchestrated balance between resources and demand. Heartbeat and health check mechanisms coordinate failover processes. A heartbeat is a regular signal exchanged between systems to confirm they are alive and functioning. If a heartbeat fails, the backup system can assume control, triggering a failover. Health checks go deeper, verifying that systems are not just running but performing expected functions. For instance, a web service might check that queries return valid results, not just that a server is powered on. These mechanisms ensure HA systems respond quickly to real issues, avoiding downtime while preventing false triggers. They are the orchestration backbone of resilient architectures. Split-brain scenarios occur when redundant systems both assume they are the primary due to failed communication. This can result in data corruption, duplication, or service instability, as each node accepts requests independently. Preventing split-brain requires mechanisms like quorum-based decision-making, fencing methods to isolate nodes, or arbitration servers that act as referees. These controls ensure only one system operates as primary at a time, even during failures. Split-brain illustrates how complexity can undermine HA if not managed carefully. Strong designs anticipate these risks and include safeguards to preserve both availability and integrity across distributed systems. Capacity planning and over-provisioning are trade-offs that influence HA. Systems must have enough resources to handle normal operations, plus the additional load during failovers. Over-provisioning ensures smooth transitions but increases cost, as some resources may remain underutilized most of the time. Under-provisioning risks outages if failover systems cannot absorb demand. Capacity planning uses modeling, monitoring, and forecasting to balance these factors intelligently. HA is not achieved through hardware alone, but through thoughtful planning of both demand and redundancy. Organizations must accept that availability requires investment, with capacity decisions directly tied to risk tolerance and service-level objectives. Testing strategies validate that failover behavior works as intended. Simulated failures, sometimes called chaos testing, purposely disrupt systems to confirm resilience. For example, administrators may disable a server to test whether load balancers and failover systems respond correctly. Regular testing uncovers misconfigurations, overlooked dependencies, and unrealistic assumptions before real outages occur. Testing also builds confidence in both the architecture and the operational teams managing it. HA is only meaningful if proven under pressure, not just assumed from design. Organizations that avoid testing risk discovering flaws during real failures, when consequences are most severe. Verification is therefore as important as implementation. Ultimately, high availability focuses on minimizing downtime and preserving service levels under adverse conditions. It accepts that no system is immune to failure, but ensures resilience is embedded at every layer of architecture. From redundancy and load balancing to failover orchestration and capacity planning, HA designs combine multiple techniques to ensure continuity. Metrics such as RTO, RPO, and uptime targets make resilience measurable, while testing and monitoring keep it reliable. High availability reflects a proactive mindset, preparing for disruption before it happens. It is a discipline of prevention, validation, and assurance, keeping critical services online when they are needed most. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Data replication is central to HA, but it involves trade-offs between synchronous and asynchronous methods. Synchronous replication ensures data is written to all replicas before confirming success, guaranteeing consistency but introducing latency. This model suits financial systems where accuracy outweighs speed. Asynchronous replication, by contrast, allows primary systems to confirm writes before replicas are updated, improving performance but risking small data loss during failures. Organizations must match replication strategies to their RPO objectives and application needs. Choosing the wrong model can either degrade user experience or fail to meet data integrity requirements. HA planning requires clarity about these trade-offs before deployment. Geo-redundancy extends availability across regions by replicating systems to geographically distant locations. This protects against regional disasters such as power failures, natural events, or provider outages. Cross-region failover requires careful design to balance consistency, latency, and cost. Systems must account for data sovereignty laws, ensuring sensitive information remains in approved jurisdictions. Routing traffic across regions often involves global load balancers that detect outages and redirect users seamlessly. Without geo-redundancy, HA protections may fail when disasters exceed the scope of a single data center. Properly executed, cross-region redundancy transforms resilience from local reliability to global continuity. Stateful and stateless service designs affect HA significantly. Stateless services do not retain user session information locally, making them easier to replicate and fail over. Load balancers can distribute traffic freely, as any node can serve requests. Stateful services, like databases or file systems, maintain internal session or transaction states, complicating redundancy. HA for stateful systems requires careful synchronization and replication to avoid data corruption. Designing systems to be as stateless as possible increases resilience, but some workloads inherently require state. HA architectures must recognize these differences, applying stricter replication and failover strategies to stateful components while simplifying stateless ones. Consistency models directly influence availability and user experience. Strong consistency guarantees users always see the most recent data, but may sacrifice availability during network partitions. Eventual consistency, common in distributed cloud systems, prioritizes availability, with updates propagating asynchronously until replicas align. Users may temporarily see outdated data, but services remain online. The CAP theorem illustrates these trade-offs. Systems cannot achieve perfect consistency, availability, and partition tolerance simultaneously. HA architectures must choose consistency models aligned with application needs. For instance, financial systems demand strict consistency, while social media platforms can prioritize availability without undermining trust. Orchestration and automation play key roles in ensuring seamless failover and recovery. Tools monitor system health, trigger failover when conditions are met, and reallocate resources automatically. Automated orchestration reduces reliance on human intervention, which is slower and prone to error during crises. Modern orchestration frameworks can integrate with load balancers, DNS systems, and cloud APIs to reroute traffic and spin up replacement nodes within seconds. Without automation, even well-designed HA architectures risk delays or mistakes. Automation transforms resilience from theoretical into operational, ensuring high availability is delivered consistently under real-world stress conditions. Backup integration complements HA designs by ensuring data is recoverable, even if redundancy fails. Redundant systems protect against component failure, but they cannot prevent logical corruption, ransomware, or accidental deletion. Backups provide an independent safety net, often stored in immutable or air-gapped environments. Integration with HA ensures backups are frequent enough to align with RPO requirements and can be restored quickly to meet RTO objectives. Without backups, HA may deliver availability but not integrity. A resilient design combines both, ensuring continuity of service and recoverability of data in the face of diverse threats. Monitoring and alerting thresholds must be tuned specifically for availability SLAs. HA depends on rapid detection of failures, but poorly tuned alerts can overwhelm operators with false positives or miss subtle degradations. Availability monitoring should include service-level indicators like response times, error rates, and transaction success rates, not just hardware status. Thresholds must align with SLAs, ensuring alerts trigger before contractual obligations are breached. Effective monitoring transforms HA from passive redundancy into proactive assurance, with operators alerted to early warning signs. Visibility and precision in thresholds ensure systems meet the high expectations users place on availability. Rolling upgrades and deployment strategies maintain availability during system changes. Techniques like blue-green deployments run two parallel environments, routing traffic to the new version once validated. Canary deployments release updates gradually to subsets of users, allowing rollback if issues arise. Rolling upgrades replace instances incrementally, keeping systems online while applying patches or features. These strategies align with HA by ensuring updates do not disrupt service. Without them, maintenance windows risk breaching SLAs and undermining resilience. By integrating deployment discipline into architecture, organizations ensure that availability extends beyond failures to include routine change management. Disaster recovery procedures must be tested alongside HA mechanisms. While HA handles routine failures like server outages, disaster recovery addresses large-scale crises like data center loss. Testing ensures that recovery objectives RTO and RPO can be met under pressure. Simulated disasters validate whether geo-redundancy, backups, and failover mechanisms work cohesively. Without testing, organizations risk discovering that HA and disaster recovery strategies conflict or leave gaps. Regular exercises build confidence, uncover weaknesses, and align operations with architecture. A truly resilient system combines high availability for daily continuity with disaster recovery for extraordinary events. Cost considerations are unavoidable in HA design. Achieving near-perfect uptime often requires duplicate infrastructure, global redundancy, and robust orchestration, all of which increase expenses. Organizations must weigh the cost of downtime against the cost of additional resources. For some, minutes of downtime cost millions, justifying the investment. For others, less stringent requirements allow trade-offs in replication or redundancy. Optimization involves balancing resource allocation with business priorities. Cost does not diminish the importance of HA but grounds it in reality, ensuring availability designs are sustainable as well as effective. Dependencies and cascading failure risks pose hidden threats to HA. Redundant components may still share dependencies, such as relying on the same power source, network provider, or DNS service. If these dependencies fail, all redundant systems collapse simultaneously. Cascading failures occur when one failure triggers others, overwhelming resources. HA architectures must identify and diversify dependencies, ensuring true independence across systems. For example, redundant data centers should use different power grids, or ISPs. Failure domains must be isolated to prevent systemic collapse. Resilience requires not only redundancy, but also diversity, breaking interdependencies that undermine availability. Ultimately, high availability is a design discipline that combines redundancy, automation, and verification. Redundant systems provide capacity to survive failures, automation orchestrates seamless failover, and verification through testing ensures systems perform as expected under stress. HA is not about perfection but about minimizing downtime and preserving service levels when not if failures occur. It is grounded in clear recovery objectives, careful capacity planning, and disciplined operations. Organizations that embrace HA design achieve resilience not by avoiding failure but by anticipating it, ensuring services remain available even in the face of adversity and disruption. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.